So hey folks, Assalamualaikum. I'm Mohammed Shahriar Al-Musakamitul. So yeah, in this video we're going to learn data pre-processing, but surely not the total data pre-processing techniques. We'll have data pre-processing be covered in 2 to 3 videos, right? Okay, so let's start. But what is data pre-processing? So earlier you have learned about the mathematics behind machine learning, basically the linear algebra, basic linear what I have to call it is regression and so on. So how it looks like, or where do we apply differentiation, integration and so on in machine learning, basically the classical machine learning. Now the thing is that we have talked about obviously some sort of metrics, right? And I also did mention that we do have lots of data, and what we do is we take this data and create some sort of metrics, and basically this is what we do. We have lots of metrics and we do solve them, some of them and so on, right? This is how it will work. Okay, maybe it will be W, and this should be M, X and so on, right? So we have to solve the solution, solve the problem. Basically maybe we want to get the solution for this, right? So yeah, this is how we are going to look into here. So you can see how will we solve this solution. We'll get the solution, obviously. So we'll have X inverse in both of the places, so it should be y x inverse M equal to y x inverse. Obviously now then comes if we can have the inverse of y and so on. Okay, this is what we have covered so far. But the question remains is, how are we going to create this matrix? Because in real life we have lots of data. We do collect that via lots of techniques, like maybe surveys, maybe Google Forms or others we do fill out, right? You may see like someone shares a form and say, hey, fill out this form and we will use this for research. What do? They basically create basically a Excel sheet. So using that, then they basically create those metrics. So we have lots of data, and then we convert them to a matrix, and this is basically our data pre-processing. Okay, basically not the whole, but obviously data pre-processing is all of the stuff we do with the data before we actually send them to the ML models. Okay, and then we send them to ML models. That is the stuff. So now we are going to just look into a data. Let's just look for here. So this is a repository link I'm going to share with you guys. So you can clone this repository or download that using the zip. Okay, so I will share the repository link. You can just do that in a local system. That means you can just download this repository or whatever you call it, a folder. Now within that we have lots of folders. So one of those are datasets. If we just go here, so we can see basically some of them. For example, here it is called loan.csv. So here you can see there are lots of values, right? For example, starting with customer ID, disbursed amount, interest, market, employment, time employed and so on. Basically what their meaning is, you can say customer ID, right? For example here, and this 0. Okay, so 0, 1, 2, 3, these are the customer IDs. Okay, these are the values. First of all, this is the you can call it a variable or label, whatever you call it, and then these are the values for this customer ID. For disbursed amount, these are the values. Okay, for interest, these are the interest rates. So there are a lot of things, and interestingly, I believe you might not understand what is happening here, or it won't look good obviously, but it is not looking good. But you can see there are commas in between the values, right? Commas in between the labels or variables. So this comma, this is because it's called CSV, loan.csv, which is CSV meaning comma separated value. So the whole file or data we have collected we have basically lots of commas here, right? So yeah, this is how it works, but it doesn't look good, so I'm going to show these in Excel. So if you just look into here, this is exactly the same thing, but yeah, but it's now we're using Excel to look into that. So if we just make it look good, having some spaces, you can see these are the values we have there in a compact manner. Okay. Okay, lost it. Okay, great. So you can see the customer ID, and this is a whole column. We have disbursed amount, we have a column interest rates, I believe, and we have market. Okay, we employment, and market is CBA, various values for market, time employed, and so on, right? These are exactly the same thing basically, but actually we are using this format so that computers can easily process that, because they are just separated by comma, so that they will just they can easily learn from that, because they just need to deal with the comma, right? And yeah, that's it. So CSV format is basically the mostly used, one of the mostly used ways. Basically you will see that someone is collecting some data via maybe Excel, and then in Excel there is a benefit, like using whatever tool you have, you can easily convert the Excel file to CSV. So that is one of the reasons, and yeah, that's easy for the computer to process. So yeah, this should be our data set. Now the question is, as I mentioned earlier, that we do collect data. First of all, this is how it works. So if we just look into here, this will be our data. We may collect that via some sort of interview or survey. Just for that, maybe we are collecting that via survey, interview, whatever it is. Okay, something. We have lots of you can see lots of columns. Okay, then we somehow convert that to an array. Okay, and there are lots of things we do deal with it before we pass that to machine learning model. So that is the whole pipeline. Okay, now what are we going to learn is, we have seen that the CSV we have has lots of obviously columns, but and obviously the data are different, right? Some had some sort of only text, some had only numbers. Here you can see for customer ID we just have 0, 1, 2 or whatever, we have just numbers. Here for disbursed amount we have some floating numbers, right? For interest rates we have floating numbers. For market we have just alphabets. For employment we have some sort of words. For time employed we have number and year and words at the same time, and that means alphanumeric words. And we have for household we have obviously only the words, and so on, right? Different types of things. So today we are first of all going to know about each of the variable type. So let's get started. So okay, variable types. So you can see variables can be of different type. First of all, can be numerical, and then categorical. The numerical can be continuous or discrete. Continuous meaning the value is continuous. You can see there are some sort of graphs which are continuous. Okay, and you can see there is no gap here, right? But discrete is like they continue here and then here and then here. Okay, so discrete. Okay, now talking about the categorical. So categorical, within that we have three types. One is nominal, another one is ordinal, and another one is date or time. Now yeah, numerical values can be discrete, continuous. So yeah, that's the thing. So categorical values can be strings and so on, date and time kind of values we can have, or we can have mixed. So we'll look into them. Okay, so for example, here are some examples given. One of those are like examples for like age. For age we can have 21, 35, whatever it is. These are some numbers, right? This age variable is basically numerical, right? Only numbers. For gender, you can see male, female. So now these male, female, obviously they are words, but they do refer to some sort of category earlier, right? So yeah, we'll learn about that. but and so on. You can just check out the example. Now let's talk about the discrete variable first. This belongs to the numerical one. So discrete, so a variable which values are whole numbers is called discrete examples. So here you can see the values. You can 0 1 2 3 4 5 6. So only discrete numbers, like customers can have one account but not 1.5 accounts. So the concept is a bit different, right? About the graphs we look into, but the value we look into. So here you can see that they're saying that discrete values are basically the values which are basically the whole numbers. Okay, whole numbers. So for example, 416205, these are exactly like 4. This is totally 4, no, nothing like 4.5, whatever it is. So we can call that 41620. okay, so 41620, whatever it is, we have some sort of for each of these values 41620, we have some sort of number of borrowers against them. So example, these we keep these values in x-axis, and some values of number of borrowers we can just keep them in y-axis. Now we can look into that these are not connected, right? The graph is not connected. As I mentioned, the graph is not connected, but however the graph is, it is not connected, so it's a discrete one, and you can just understand by this as well. And continuous variable. So continuous variables are basically a variable that may contain any value within some range, okay, so that can be. So here you can see interest rate, like for example, interest rate can be continuous, and interest rate can take in principle any value within the range. Okay, for example, here you can see that we have 15.8, 11.67 and so on, right? 15.8 should be something like this. 11.67 may be something 11.67, and 9.27 maybe here. Sorry, 9.25, 6.24, just assume 6.24, 19.52, maybe here. Okay, so there are lots of floating point values here you can see, and again these are represented in x-axis, and in the y-axis we have some number of loans for them. These are basically the ranges. Here you can see for range between 5 to almost 20 or 25 to 30, I believe, almost 30. So for them, this is basically interest rate. You can see there are various type of interest rates, and interestingly, if you just look into here, you can see these are the stuffs here. So you can see interest rates 15.484 and so on. There are lots of ranges, right? Obviously the floating points, and that is not directly a integer value. These are floating point values, and for them, for these interest rates, we can see the disbursed amount or loan we have, right? So if we plot them, the graph will be, so if we plot them, I believe the graph will look something like this. But earlier, number of borrowers, if we plot them in the y-axis, and the number of installment accounts opened in past 12 months, if we have these two kind of variables or labels in x and y axis, this kind, the graph looks like that. So it's basically plotting two variables and look like how the graph looks like. So this is how we can say, okay, this is a discrete kind of these are discrete kind of variables, these are not. Okay, now there is another which is called the binary one. So when we have loan defaulted, which is which takes one of two possible values, for example 1 or 0, or defaulted or non-defaulted. So when someone says, hey, this person is loan defaulted or this person is not, so either the person will be loan defaulted or non defaulted. That's it. So we have these two variables, and we can just choose, okay, hey, so here you can see we have almost lots of people who are, if we consider 0 as non-defaulted, so non-defaulted, and only few people who are defaulted loan defaulted. So yeah, this is basically about knowing them. Okay, now talking about the categorical one, we have just learned about the numerical one. So the categorical variables, if we look into them, so the categorical values are basically, as you can understand, they are related to words and they do define some categories. So first of all, we have ordinal variables. So what are the ordinal ones? So here you can see categorical variables in which categories can be meaningful. It's interesting that the categories are meaningful. For example, when someone says that, hey, you have got A in exam, it means good, right? I mean, obviously, some places it's like CGPA or GPA 4 or 3.7, right? B is less than that, and so on. So these A, B, C are meaning something. That A means the best result, B means okay, not that best, but obviously good. C means okay, not that good. Or fail means obviously the worst, right? So this is meaning something. So okay, for example, days of the weeks, weekend in general, like in some places the starting of the week start from basically Monday. You may hear that in some organizations, which is basically the remote organizations or who basically focuses on the Western countries. You will see that they have a holiday in basically on Saturday and Sunday, so they start from Monday. So one is basically meaning for, if we just look into the days of the week, if we say it's one, just meaning the Monday, and if we are saying 7th, which is basically Sunday, because the 7th day is Sunday. This is how it works. But in Asia in general, it is basically 7th is in general the Friday, and Saturday is basically one. So it depends, but they are actually meaning something, right? Days of the week, if we have one, this is meaning something, this 7 is meaning something, right? This is ordinal. And we have obviously special cases like the categorical variables where categories are encoded as numbers. Okay, like for example, gender may be coded as 0, males, and zeros for males basically, and 1 for females. So it can be, but in general this is encoded basically, because we can, for example, we for gender, like we have just written let me just write that. So for example, if you just think we have gender as a whole, so we can have that as male or female, right? So sometimes we can encode them to numbers so that we can do the machine learning process, right? Right. So now let's talk about the ones. So if we look into that now, as we talked about the categorical variables, right, some of them. So mentioned before, this can be ordinal, nominal. So we just look into here, ordinal, nominal, or date or time centric. So yeah, that's the one. We have just talked about the ordinal one variables from here, and you can just look into them. And the nominal one. So yeah, the ordinal values, we have just talked about ordinal, but let's talk about the nominal one. So what is a nominal variable? So if a variable like country of birth, okay, this can be a nominal one. How? Because like you see, show no intrinsic order of the label. So like for example, A, B, C and fail. So obviously you know that A is of rank 1 maybe, or high rank, right? B is of rank 2, C is of rank 3, and so on and so forth, and fail is maybe rank 5 or so, for example, just if you just grade them depending on the ranking or so on. But if we have country of birth, Argentina, it can be, for someone it can be Argentina, for someone it can be England, for someone it can be Germany, but it does not make the person different, right? It is basically okay, the region is different, that's it, but there is no ranking here, right? Same as the postcode. If we have a variable or a column which has the postcodes, obviously the postcode refers to some place, but it depending on the value, like maybe some thing is 1809, for some 1800, this 1800 is not higher rank in higher rank than this one. It's basically defining some area, right? Same goes for vehicle make, depending on these ones. Now we have again talked about the special cases, right? So we have already talked about that, the encoded one. Now let's talk about some example. For example, if you just look into here, I've just taken this screenshot from that loan CSV we have checked. So you can see that for these variable householder, we have rent owner, mortgage, and so on, right? So these like example, basically the mortgage and the rent owner or other, etc. Here if you just keep up them here, like mortgage, rent owner, own or other, and number of customers, so obviously we have these values from here, but number of customers is from another column obviously, and we keep these in x-axis, and number of customers from customers in the y-axis. We can do that, and we can have this kind of discrete kind of look like, right? So the point is not the how the graph looks like. The point is that okay, the rent owner, etc., that actually defines something, right? That is some sort of values. These are categorical actually, to be honest. Now again, talking about the loan purpose, here you can look into here you can see debt consolidation, then car purchase. So the reason, right? So the reason, so as a whole, it does not make it different, like a not rank, right? Obviously we have some sort of rank here, but meaning something like okay, rent owner and so on. Or you may also say there is no rank here. It is again true for here as well, but yeah, obviously here you can see there are lots of reasons. It can be totally different, random as a whole, so it does not belong to anything. So we may call this as I believe the ordinal one, but we have to call these as the nominal one, the loan one, the loan purpose, only this one. I'm talking about loan purpose, not the graph. The graph is different. This is totally different one. Okay, the home ownership, for example, or householder, this is ordinal, and the loan purpose is nominal we're looking into. But the graph is the graph can have some relation obviously here, so we can see some discrete one sometimes. So yeah, that the relation or something that's totally different. Okay, so we're just interested with the variable, okay, or the label. Now let's talk about the time and date and time. So here you can see date and time one, which is within the categorical we have seen earlier. So date and time one can be divided into only date, or only time, or only date and time combined. So here you can see date of birth. Here you can see we have just numbers 29 and 08 and 197, right? But for date of application you can see number at the same time month, right? Date and month. For time of accident we just have numbers, and for payment we have just numbers. So in our loan one, if you just look into here, this one, if we say here, you can see we have both the date and time. Not like date, okay, we don't have date and time as a whole, but we have only we have alphanumeric here, right? So we can call, we can keep that within that, but like 5 years, 6 months, or at this PM, it totally depends. It's not totally the only the numeric one, right? So why are we learning this? Actually, this is just to understand, okay, these kind of things can happen, but it is, to be honest, there is no direct thing like relationship with machine learning, to be honest, directly, but it's to understand, okay, what kind of column values or variables we do have, we can have. That's it, simply in general. But we will start with some sort of relationship about the data set within a while. Okay, now talking about the same thing we have just learned within a while, that is, you can see the date issued we have in the loan CSV. So it's totally the date, right? So here the date variable, so you can see here within that it's a loan issued the date when the loan is issued, and last repayment date, which is not included here. If we have that, let's just look into that. Last repayment date. Okay, here you can see last date payment. That's it. So it's again some sort of date we have, so it's like date variable. So yeah, so we can have some sort of relationship with that, like for example, if we just have that date issued or last repayment or payment date in x-axis, and in y-axis maybe we can have disbursed amount. Okay, so we can have some sort of relationship, and that's it. Just looking into the relationship with some other thing, so we'll talk about that. Okay, another thing is mixed variables. So variables can be mixed, as mentioned earlier. So this is the one which is like date and alphanumeric as a whole. So for example, if you are flying by plane, or maybe if you are in a Titanic or so on, or in a ship basically, so your seat will have basically an alphabet at the same time in a numbers, which is alphanumeric. So you will see that at the same time, sometimes postcodes are alphanumeric and so on. So it does not it does not make it, I believe it is a factor to differentiate, right? Like for example, if you're flying by plane, you will see, if you just enter into the plane, there are like A, B and so on, right? And so on, you will see A, B, C and so on. Then within A we have A1, we have A2. So it is meaning something, right? It is meaning something, so we can have that. So this has some meaning, right? Something, and depending on that for B and C, and it goes on, something like that. So it's meaning something, obviously. Great. So it's basically mixed variable. Okay. Then missing data, that's the interesting part, and that's the starting point of today's session basically. So we have to understand the important factor. Now if we just go to the loan one, here I'm just trying to look for some blank spaces. Interestingly, here it is, you can see here we don't have value for this customer ID. Okay, 19 here. Okay, maybe it can here you can see it happens again for customer ID 92. So yeah, this does happen. So missing data, so this can happen. Okay, in a CSV this can happen, like someone might not have that value for that, or sometimes mistakenly it might happen. So value is missing because it was forgotten or lost or not stored. Okay, a variable is created from the division of two variables, and the denominator takes 0. A lot of reasons, these are reasons that can happen, like don't exist or lost or not found or not identified. These are the reasons the value might not be in a CSV. So, but the impact is important. You have to understand the impact, like why is it important to acknowledge that we don't have a we have some missing data, and how it impacts. So in our machine learning models we will use scikit-learn, which is this is how you pronounce, which is scikit-learn. So you can see, so we will use these the models, machine learning models from here. We have this is basically library, so we'll use that. But if we have missing data, we cannot use that scikit-learn properly because it is incompatible with scikit-learn. At the same time, missing data imputation may distort variable distribution. At the same time, it affects all machine learning models. So that's important that we have a lots of data, but here we have missing or something, like assume an array like this, like we have a missing data here, missing. So how can you multiply with this? What will be multiplied? We should replace this missing value with something, maybe 0 or whatever it is. So we have to deal with it. We have to know how to or what to place here, right? Because there might be some other value which is dependent on it, because we have to multiply or add or so on. So we have to deal with that scenario. We have to deal with the missing data, because we are basically we have a lots of data. We are just converting that to an array, and if we don't deal with the missing data, that will the missing data will be in the array. So there will be some sort of data missing out there. So and there is lots of values out there, so it has to be multiplied with the array and so on. So what will happen with these values? Like the value may be assumed this should be multiplied with this. Now what will like for example, we have 2 and we have 2, like what will be here, right? So we have to understand what we should have or how we should deal with the missing data. This is one of the process of our feature engineering. Okay, so yeah, that's it. So here is the there are few actually I would say classification of the missing data. One of those are missing data completely at random. So it can happen completely at random. The probability of being missing is the same for all the observation. There is absolute no relationship between the data missing and any other values observed or missing within the dataset. So what are we trying to say? That means we have assumed that we have taken some sort of interview, and as I mentioned here in this value there is some sort of data missing here, like something maybe it's totally blank, right? Where it can happen. So it may happen that this is missing because maybe there is some mistake. It's totally random. This is like someone was typing, he was including all of the value and mistakenly he just missed it. It can happen, no problem. This is called MCAR, missing data completely at random. There's another thing which is called missing data at random, which is again almost the same. The probability of an observation being missing depends on available information. The probability of an observation being missing depends on an available information. So what we are saying is, here you can see some random man and woman didn't want to share their weight. That's is basically observation being missing depend on available information. So it depends on the scenario. Here you can see what happens is this data was collected from some male and female, where the interviewer asked, hey, can you share your weight? So some male didn't want to share the weight. So one of those this female here, right? So assuming here it was totally, there was no relation, it was just by mistake and it can happen. But here they didn't want to do it. Okay, so here you can see we have 2 NA for the man, like almost for within all of the men we just 2 NA, and it is 33%, and within women it can 50% of the women didn't want to share. So they didn't want to share. That's one of the reasons. But it depends on the scenario. Again, we have another one which is called missing data not at random. So again, the thing is it depends. You can see the male. So you again cannot define a person, rather you are defining a gender. Like like 33% of the men actually didn't want to share, and women 50% of the women didn't want to share, and so on, right? You're defining a male, but sometimes it can happen that you are defining a particular person, like maybe Rahim and Kareem and so on. We have some people, Rahim, Kareem. So you are trying to take an what I would say is an interview on the state, mental state. So the target is depression. So everyone said yes, our target is to reduce depression. Maybe it can happen. So number of clinic visits. So how many clinics have you gone for? A number of sports classes weekly you have attended, and so on. Here you can see there are like number of clinic visits, which is NA. So here you can see as NA as well. So here this NA is referring to something else. Here they didn't want to share. So it was meaning like, okay, there is no value, basically 0. They didn't want to share. So what we can do is, we can consider when we are working with the machine learning model, what we can consider is we just don't need to take the values of this person, right? For example, these men didn't want to share his weight. Okay, let's just don't consider them. But here in this scenario, this NA might refer, that means this person doesn't want to share the value here. So this is referring to, again, the depending on the scenario, as we are talking depression, can be something related to depression, because this person is depressed, so he doesn't actually attend the sports class, so he doesn't go to the clinic visit. So this NA might refer to, okay, that is one of the reasons leading to the depression. Okay, I hope you understand. So we have to consider these values, because these NA might refer to that these are the people who and these are the reasons why this person is depressed. But here we can just avoid this NA, like, hey, this person didn't share the weight, so maybe our goal is to get the average man weight, so we don't consider these values, because okay, this person didn't want to share, okay, no problem, we'll just take the people who have considered giving their weight. But here we have to consider this differently. So it's important to understand new data, so which most of the folks who learn machine learning just learns the library, just implements machine learning model and they're gone. So it is not how machine learning works. You should know the distribution, probability. Is so interesting. To be honest, most of the folks don't try to look into that. Okay, there is another concept which is called cardinality. So cardinality is the number, basically the number of different labels we have. So for example, here we have gender, right? So you can see we have just male, female, right? Okay, you might ask the question like, hey, how many genders there are? But yeah, obviously there are two genders, so we have just provided male and female. So what we can say is this gender label has a cardinality of 2. Why? Because it has two different values, that's it. Here for vehicle make, here you can see the basically made by Mercedes, Ford, Renault, Seat, and so on. So here you can see one, then different 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have vehicles made from 9 different organization, right? So the cardinality of the vehicle make variable or label is 9. That's it, simple as that. So why are we bothered about it? It's important because you have to understand that, just simply understand, like you have a huge data set and you have just male and female, great. So interestingly, I have previously talked that we can convert this male or something, we can convert this to encode, right? Encode to something maybe 0 or 1. We can do that, right? I did mention, right? So what we can do is, interestingly, maybe there might be a scenario when binary classification model is what we're looking for, we're just looking for gender determination or something. You can easily take consideration and encode them as 0. Like for example, you are just saying, hey, for male we are just thinking it has a value 0. For female, we are considering the value should be 1, because they are always correct. So yeah, we can have that female. So we can just for all of them we can just have 1, 1, 1, 1, 1. We can do that. But for days, you can see we have 9 different values. So in a data set, it is basically the data sets do remain to be like we can have 9,000, 1 million, billions of values. We can have that, right? So maybe in this gender, if the cardinality, that means we have just 2 different values, it's easy, we can just convert to 0 and 1, and we can do something like called binary classification. We'll learn about that. Okay, binary means 2, so we will have classification, or we will have detection of 2. Like there will be a problem and we will be asking like, hey, is it a male or female? So we can say male or female, easy. But these kind of things, if we want to encode it, these kind of things as we have lots of value, lots of different value, we have a cardinality of 9. So maybe we can encode them as 0, 1, 2, and so on, and it will be like 0, 1, 2, and 8, right? 9. So it can be multi-class classification, it can be used. So there are a lot of things, in a lot of ways we have to deal with it. So it's interesting to understand why and how we are dealing with it, rather than creating a project. Okay, just focus on that. Now, what's the impact of cardinality? You can see that strings are incompatible with scikit-learn. So cardinality, so here you can see if the values are strings, so in scikit-learn it cannot work. So why is it important? Just a moment back you saw me that the string I had, the male, female, I just converted it to 0 and 1 values into number. So if you want to work with scikit-learn, you have to convert that to numbers, right? Or different format. And again, uneven distribution between training and test sets, it can happen. So it is interesting. We'll learn about that here. Rather than now overfitting in tree and based algorithm, we will learn about that. And okay, so these two are what we are going to learn from here. Now let's talk about the strings and categorical encoding. So scikit-learn as does not support string as input. So as it does not support string as input, for example, male, it does not support. So we have male as gender. So categories must be encoded as numbers, as I mentioned. So we can encode them, maybe for male we can encode them to 0. Encoding techniques impact feature space and variable interactions. So it's interesting. So female as 1. So yeah, we have to deal with it. So scikit-learn, as we are going to deal with it, scikit-learn cannot work with that. So we have to make it, because the thing is, as a whole, you are multiplying like matrices. Matrices don't have strings, they have value, so we have to convert it to value. That's the concept. That's why scikit-learn does not or is not able to work with it. Now let's talk about this interesting factor. This is very interesting: uneven distribution between train and test dataset. So let me just tell you what is train and test dataset. Sometimes if you are totally new, you might not understand about it. So let me just give you okay, so here you can see we have from starting from 1, we have how many data. If you just look into, if you just go, okay, we have how many data we have. Okay, so 1000, I believe. No, okay, it's huge. It's not 1000, it's 10,000. Okay, so we have 10,000 values here. So what will happen with in the scenario of this kind of things, you do understand, right? Because it's not a small, so there are a lot of things we have to deal with, a huge data set. So it can happen. It's not 10,000. In real life we have huge thousands and billions, so it can happen. Now the factor is, what we do is we have some sort of data, right? What we do in general is, let me just give you a brief what happens in real machine learning. That is, we have a huge data set that can be let me just use this one to make the data set. Then we just convert them to 2 different arrays. One array is where we have 80% of the data from here, and one array is where we have 20% of the data, or you can call the data set small data sets. This is called train data set. This is called test dataset. So what are they? So train dataset is basically like you have maybe 10,000 okay, 10,000 data here. Okay, 10,000 data, huge. So the goal is if we have 8,000 data here and we have 2,000 data, so the goal is we build some sort of model, or we use some sort of model here. Then we train that we train the model on using the training data set. Okay, just understand that by some sort of exam. Let me just give you the brief of something. For example, you are a student, right? So and you have a teacher at home. So he basically, what he does, he basically trains you at home, like teaches you, right? So this is what it is. Then after a while, so the model is basically you, assume that. So you have been trained with some sort of materials, like the preparation you need to take, you have taken that using maybe some sort of instrument, okay, or necessary study, whatever. Maybe assume that like it is you, the model is you, and you have exam on, you have 5 chapters in a book, okay. The exam is on obviously the exam is on all 5 of them, but you have prepared for all of them from 1 to 5, sorry, 1 to 5, from you have prepared from all of the chapters. So you have done that, you have trained on them. Now in the test, okay, you are done, you are good. Now in the test, what will be done is, you will be asked, maybe the teacher asked, hey, he asked questions from chapter 2, chapter 4 and chapter 3, okay. and he will then say, hey, how much did you learn? So then the model will say, this is the okay, you will be asked from these chapters, and okay, he will check. Obviously, if you can answer all of the questions, the teacher will give you 100 marks. In machine learning, this is the goal. This is basically what we try to look into. If all of the prediction are correct, that which we were supposed to get, we do get 100% accuracy. In general, it's tough, but this is how things work. So you will see sometimes that the accuracy is 76%, 87, or whatever. It means that 85% of what you are saying is correct. That's it. Okay, this is how things work. Let me just give you some example more. Assume that you have y and x, and it is 2, 5, 3, 9, 4, 6. It's totally random. Okay, just don't think it much more. And 7 to 11. Okay, it doesn't look like 11. Let me just remove that. Let me just 11 to this kind of, this is a data set. Assume that we just have 2 columns. Okay, now we can see 1, 2, 3, 4, 5. Okay, 5, right? Rather than that, let's just make it okay, it's not a problem. Just assume that this, we just want to create this is a data set. So from here we will just take majority of the values, which is from here. So this creates a training data set, which is 2, 5, 3, 9. As we don't have any missing data, so we are just taking that, and this is train. Okay, training data set, and this 2 is testing. Okay, which is 7 to 11 2. Okay, this is testing data set. Your testing is this training data set. So now you have a model, for example. It's a model. We are not bothered about how the model works, what it is. We'll know about it. We just think, you have to think it's just like black box, like you are not bothered about whatever it has within it. But you know is when we just pass this train to the model, what it does is it learns. What it learns that for like 4 or 5, like as it was 2 and it was x, like for the value of 5 we should have the value 2. So it is learning that for the value 5 we should have value 2, like 5 is x and y, and for the value 9 we should have the value 3, the value 6 we should have the value 4. So this is how it is learning. Okay, you just understand what it is. So it tries to learn like how the relation came up. Like maybe it is trying to find, like I have mentioned earlier, x and y. If you just define it, maybe these are our points. These are our points. 1, 2, 3. Okay, no problem. This can be our point. It doesn't look good though, but yeah, this can be a point. And now it is trying to decide a proper line between them. Maybe this is a line, although it doesn't look good, but okay, let me just draw it properly. Okay, assume that it's on x-axis, y, like 2, 5. I know this is totally random, like 2, 5 for example, like 2, 5. Then sorry, oh, I made it. So 5, it should be 5 2. So it should be 5, then 2, and 9 3. It should be 9 3, and 6 4, 6 4. Just assuming that. Okay, so maybe these are our plots, x and y. Okay, now maybe I'm not sure, because just guessing that maybe this is a line that it generates. The model generates after learning the relationship here. Now the goal is, when we pass the test data, I previously taught you that, like what we do, like this 2 is our x right here, because we are drawing x. So this 2 will be passed because we are passing this. What it will look into is, it will pass this 2, like from here it will say go to 2, and it will try to look if we are getting value 7 or not. it will maybe get this value. It will say, okay, the value for 2, the y for 2 is maybe what we can is 1, right? Maybe it is getting like we have here is 2 7 because x and y. If we look for in the test set, and we have is 2 11. I believe it cannot exist at the same time. Okay, what we can do is maybe 4. Okay, 4 11. Okay, so this is in the dataset. This was the real truth. You have to understand that we are actually learning from the dataset we really have. That means it's the truth. This is a survey value. Okay, this is like 2 7 4 11. Okay, no problem. Now from the model we are just using only this x value, and we are saying we can find the y. So what we found is for 2 we got the value 1, but in the real data set, like here, I believe it should be 4. So in the real data set you can see it is 2 7. That means this model or this line is not learning properly. It is doing very bad taking very bad decision. Like for example 4 11. So for 4, if we just look for 4, I just forgot, we should have 5 9 6, right? 5 6 9. Okay, so 4 it should be here, something like that. So it's saying it should have 11, but it might get the something like maybe 1.5. So it's getting for 4, it's getting 1.5. But here in the real truth, it was 411. But we are saying our model says for 4 we should have 1.5. That means this model is doing very bad, which should get 0% now, because you can see if any of those like we have 2 values, right? If either or any of them is true, like maybe if it would have got for 2 it would have got 7, we would have said like we have a 50% accuracy, because one of the results are true, 50%, because we have 2, so within that we have 1 correct, so we can say obviously 50%. So this is how accuracy is actually understood, because this is how it works. So I believe now you understand what test dataset is, what trained dataset is, and how we get the accuracy. And this is model accuracy, because the better the model is, the better it will easily understand the features from the data and create a line or so on. It is basically for the linear regressions and others. Linear regressions, basically there are different models which works differently. This model basically is a linear model, so this is how it works. Okay, I believe you are now very much confident about how machine learning models do work. Okay, now let's cover the remaining topics quickly. Now, as I mentioned, so here you look into that you have a huge data set. Great, you have a huge data set. Now you can convert them into train and test, as I mentioned earlier. But sometimes you may see that like there are some common values or whatever it is. You can see uneven distribution between train and test data sets. So here for example Mercedes, Ford, Renault, then Citroen, Kia, Nissan. So they are different, right? And you may consider like some of them as important one way, maybe like the Mercedes, Citroen and Nissan, assume that. But here if you just look into here, do we have Mercedes here? No. Do we have Citroen here? No. Do we have Nissan here? No. That means we are saying that we're training, or we are using this training data set for the model, and the model is learning for this specific data. But when we are not passing these, that's obviously an issue. And like for example for said we can't see the value here, we can't see the value Toyota here, we can see the BMW value here. So when we will use this test data set, it won't be very good for this specific ones, right? So it will be saying like, hey, or the result will show, basically it will say like we will have a very bad result. So what's the impact on it? So when you see some labels may appear only in trained data sets, like some labels only appear in the trained data sets and which does not appear in the trained data set. If that happens, the model overfits. We will learn about this concept, overfitting and so on later on. You will see sometimes the accuracy is so high and so on. We will see. And some labels may appear only in test dataset. So when some labels only appear in the test dataset, but it is not in trained dataset, the models will not know how to interpret that values, because as mentioned, some labels only appear in test dataset, specifically say Toyota and BMW. So the model learned for these values, but when you say, hey, tell me the value for this, it will say, I don't know, because I was not trained on this data, right? So interesting. These are the importance. And talking about another one, which is cardinality and overfitting. So cardinality and operationalism. So the overfitting is for the, if we have more some values which are only the appear in the trained dataset, we have that. And cardinality when the operationalization is basically for this one. Okay. Now the thing is, let's talk about the real labels. Sometimes we can have some real labels. Okay, real labels are those that appears only in a tiny proportion of the observation in data set. Okay, for example, for the variable city where a US citizen lives, like New York is a frequent category. Many people live in New York. Okay, live in North is a rare category. Few people lives there. So okay, it can happen. So we'll learn about that. For example, let's look into here for assumption. Just look into that these greens are, we have two variables, gender and vehicles here. The vehicle may show some labels, they are less frequent, right? Like Mercedes, Toyota, Nissan. So here you can see this Ford, Renault, Kia. These are common in both train and test dataset. That means, okay, these are common. But there are few like less frequent values, like basically maybe very less in the whole dataset, which are like Mercedes, Citroen, and so on. You can see, you can't see any Mercedes here and so on, right? These are very less frequent dataset. But Ford, Renault, and Kia are more frequent dataset. Okay, it can happen. So these kind of things, like these less frequent, are the real the basically values, or you can call labels. Okay, now there is a reasoning why this thing actually creates the operational costing and so on. Okay, so as mentioned previously, that the real label again works something like the previous one which we have learned here, the cardinality, right? If we have this kind of scenarios, okay, some labels appear here and some label does not appear and so on, this kind of scenarios, the real label actually works for that. When real label appears only in the training set, so assume that in the training set you can see Mercedes, Citroen, Nissan, these are real labels. Let me just write it R here. Okay, just assume that they don't exist. Okay, so here you can see in the train set we have some real labels. Why? Because these are very less in number compared to other values, because you can see Ford, Renault, and Kia, these are here we have, but these few values, there might be some values, we can call it rare because they are very small in numbers. So it's said that when real labels appear only in training set only, okay, the problem is the model learns pattern that is specific to those real examples but don't generate to the real world. So what does it mean? That means as I mentioned previously, what we do pass this training data set within this model, and the model basically learns the pattern and so on. So it is ready to give some output for these three as well. But when in the test data set, you can see, okay, they are not even used, right? So, but the point is, assume that the goal is to know the connection between Ford, Renault and Kia, right? So the value for them with the gender, maybe like who buys the Ford card, mostly males, and for Renault males as well, Kia for female. Okay, so you can see Kia female, Renault male, Ford male. So you can see the connection that the most males do buy Ford and Renault. But so this can be the thing that the model learns. Okay, males do prefer Ford and Renault, women this. But the problem arises is the model is again learning for Mercedes, Citroen, and Nissan. So if someone asks, we have a like male, what should he prefer? The model might say Mercedes because it's for the male, Ford, Renault at the same time. Yeah, that's it. Those three answers, right? But which is not what our goal is. So that's the point, that if we have real labels, it's the issue because it might not be our goal. So it can learn for that more values, but it's not necessary. Again, when real labels appear only in the test data set, so again the model has never seen examples of this data. Now we just have to reverse it. Now we are assuming that we just don't have real labels here. We just don't have these values. Okay, we just have them here. We just have these values. We just have these values here, but we never did have these values. We just have the three values here. So it learned for Ford, Renault, and Kia. Okay, it's perfect. Now it knows for male, they prefer Ford, they prefer Renault. Okay, and it learned that for female, females do prefer Kia. Okay, now you came up and said, hey, for this car, is this a male or female who prefers that? So it will say, hey, I just learned for these cars. Where did we get this set from? That's interesting, right? So this kind of scenarios we do have. So depending on that, or import and a lot of things, right? Again, real labels and deriving information. So here you can see. So assume that there are lots of actually what I would call labels we have, okay, or labels we have within a column. So for these labels we have some sort of percentage of houses per category. So for them we have these as well, and these as well. We have these kind of things. So for them, if you just plot them, you can see there are lots of graphs basically. But as we have a lots of labels, you cannot see a proper information. Sometimes it's good, sometimes for these it's good, medium it's better, and then it's far more. So there is no sort of real thing you can learn from here. It's hard to understand the true effect of the real label on the outcome. So which are the real label here? So here we have you can see this one, then Simlock, I believe this one, then this one, I am shocked. Okay, to look into that as well. This one, a new level. If you just look into here, okay, so if we just consider them as a real label and keep all of them, like take all of the values for them, like you have maybe values for Stuka as 7, like, and for that it is 9, 8 for 1, 2, 3, like for example we just take all of them and take the average, sorry, not the regular, take the sum and so on. Here we just replaced all of those with this real, like we just took the sum and we considered them as a new variable and then created the plot. Now you may see some sort of connection. It is started from top, then is decreased, had some connection, then increased. So yeah, so we have to deal with these cardinality in real life. So now the interesting point and the last topic of today's session, properties of probability distribution. So this is interesting, that the probability distribution basically indicate the likelihood of an event or outcome. This is a distribution basically which refers to the likelihood of a scenario. Now you know we have been dealing with y, x and so on. So we are basically dealing with that, right? The likelihood of getting, maybe we have 2 and 7, the likelihood of, our goal is to get or create a connection of likelihood of getting 7 from 2 or something like that. So you can see px equal to the likelihood that random variable takes a specific value of x, px equal to this. We know this thing by probability of x, right? Probably we just call it px, right? Probability of x. Now the sum of all the probabilities for all possible values must be equal. These are some laws. Sum of all the possible values, and the probability for a particular value or a range of values must be between 0 to 1, the probability. So it should be within 0 to 1. P of x, the value should be within 0 to 1. Okay, these are some laws for the probability distribution. Now this probability distribution can be actually classified into discrete, continuous. Discrete can be like binomial and Poisson, and for continuous you can have Gaussian, skewed and many others. So the graph for them can be found here. So here's a link. So if you just go into the link, I will share the link. You can see different kind of graphs for them, the probability distribution, but we are much more interested about the normal distribution, which is called Gaussian normal distribution, and we are again very much interested about the skewed distribution. Okay, so Gaussian distribution basically looks like that, like it's a symmetric one. You can see it's in the middle, and it's a very good number, very much value in the middle. So you can see like variable values, for example, maybe you have some variable and the variable values are 1, 2, 3, 0 and so on. So you can see most of the, and for those variables there might be some sort of frequency, maybe frequency meaning maybe some sort of value against it. For example, we can say we have 0 40 times, you can say we have 1 for 35 times, we can have 2, we have 2 for 15 times. So for we have -1 for like -35 times, we have a -2 for -15 times. It can happen. So something like that. So if you just plot them, you can just look into something like that. So here it is symmetric, because if you just you can see 0, 1, 2, 3, we have 3 out here, we have 3 out here, and it looks like it's divided, it can be divided into 2 equal portions, so it's symmetric. But we can have another kind of graph, which is skewed distribution. Skewed distribution is, you can see a distribution is skewed if one of its tail is longer than the other. A left skewed distribution has a long tail, also called negative skewed distribution, and a right skewed distribution shows a long right tail. Okay, long left and long right. So if you just look into or look into what they look like, here you can see this is the right skewed distribution. Okay, so we said in the right skewed distribution you have a long right tail. Okay, so you can see a long right tail. So this is the tail, right? In a fish, what do we have? We do have a tail. You can see this kind of thing. So here, assume there is the central and there is a huge tail, long right tail. But here it's the left tail is huge. So this can be some sort of we can plot them and we can see this kind of distribution of values. Okay, distribution of values, obviously in y and x axis, obviously when we plot them. So in basically the symmetric distribution, the mean, median and mode values for particular data set, basically this is important because in a data set we need to know about the mean value, median value, mode value and so on. These basically these are another different concepts of mathematics, obviously. If we just see if we have same values, we can have symmetric distribution. If you have different, we can have different, like for example in the right skewed you can see mode value is obviously greater than mean or greater than median. Okay, so this is huge and less huge than very less, right? Then here as well the mode value is obviously greater, but then again the median value is what. So yeah, this is how things do work, but it again depends on the, like if we just different, here we have x and here we have y, right? So here we have something. So for x you can see the x is increasing and here, but the value is decreasing. But here you can see For x we have y, x for here you can see for x it's increasing. So this is how things do work. There are a lot of things from the graph you can see like what kind of relation do we do have. Now what's the relation about, or why are we bothered about it? That is something we need to know. Okay, the concept of that is basically related to some sort of thing called outlier. Okay, an outlier. What is an outlier? So maybe you have learned about outlier from our model or mathematics for machine learning models basically. So maybe if you have looked into the datasets I did mention, like maybe we have something like this and this. So they are using the data, they just learned, okay, this should be a line which is very much near to these values. So the goal is, maybe if someone now provides an x for particular, so it can just say the value y for that. Okay, right. Okay, just not that line. Okay, this is how things will work. So I believe you have understood. For a particular x, our goal is to get the y. Okay, great. So y, but you can again see that these points are very near to this line, but this point is very far away, right? Very far away from the particular line. So this can be called as an outlier. That means okay, this does not belong to the data set. Okay, this can happen. Sometimes this outlier is very important when, like for example, you have a credit card and you can see, okay, there are some transaction 100 200 of something. Sometimes you just saw like, hey, you have a transaction of 1 lakh that maybe for 10 years this person just deducts 100 200, but you just saw like, hey, someone just started to ask for 1 lakh. Then it is important to understand, maybe it might be an actually a fraudulent stuff, like maybe someone is trying to steal some money from the account. So the bank should start to like, hey, stop the actually transaction, right? So in this scenario, but for a sometime maybe the revenue forecasting, sometimes the revenue is quite good and there are some special point when the revenue is too bad, you can just ignore them, right? Okay, situations do happen when the revenue is too bad, but we have to take the generalized values for the scenario or month and so on. So it depends on the thing. Now the concept comes up is when we do have this outlier. So in linear models you can see like these points are very near to this line, specific line, very near, but this point is very far away depending on compared to these scenarios. So this is an outlier. Again, we can have something called error boost on the models. So in this scenario we may also have the scenario. Now let's talk about the normal distribution. So here you can see in normal distribution, let's talk about the features of normal distribution, and or we can call our basic talk is where the data remains. In normal distribution graph, if you can create the normal distribution, you will see 50% of the data remains here, within here, okay, and the others do remain within this. So you can see this is 3, so almost like 0 1 2 3. So from 0 to 3 and from 0 to -3 we have the value. So anything outside this point, in general, all of the values do remain here. Outside them are outliers, like here, values outside. Okay, values outside. So the range of this can be like from this to this. Within this we are perfect, but outside them, outside this range, we are not perfect. Okay, I just write it like this. Now for this is how we can deal with it. So these on this thing or scenarios, the positive skewed or whatever you call it, right skewed. So we have a new concept which is called interquantile range, which we get by minusing like getting the 50% value. Okay, so here you can see that we have 50% value here, so we can call it interquantile range. But for skewed ones as well, we can get that by 75th quantile minus 25th quantile. That means 75% value wherever we have, and we need to minus them from 25% quantile. So there are a lot of mathematical stuff. So the goal is not here, the goal is to look into here. Just look into here. There's something called box plot. So box plot. So using that, we can define where the outlier may live. So if we have a box plot, just look into here. So what we are saying is that assume that in box this is a box plots this kind of box. Within that we have some sort of median. The outlier may reside here outside of the total range. This is the minimum range, the maximum range, outside of the range. So this is our normal distribution, right? If we create if we get the box plot for this distribution, we will have something like this, because as you know, I mentioned interquantile distribution or interquantile range basically remains in the where we have 50% of the data. So you can see here we have 50%, so here it is IQR. You can see it is IQR and this is the maximum, this is the minimum value. We can have that, and I mentioned again that outside the maximum and minimum we do have the outliers. So here you can see outside maximum minimum we can have outliers. So this 3D box plot again mentions like these are the points where we can have outliers. Exactly, this is what we said here, outside. Again for the whatever we can call it, here we have left skewed dataset. The dataset is basically plotted something like that, like here x-axis, this is y-axis, something like that. Okay, so we have to visualize it differently. So here you can see the maximum of the values we do have is here. So the box plot like this, actually if we just create the median value or the maximum, the values, majority of the values do remain in this portion. So for that, so yeah, this is the maximum, minimum, and so on, we can have that. So the outlier, again as mentioned, this will be outside of that, so the outlier should be outside. So this is how we will learn about these concepts later on, like how we can use them. So but before that, let's just end up with this concept, which is the linear models we've learned earlier. So you might have seen the y equal to something I have covered there, some sort of constant we have here. The basically these are our consistent coefficients. These are our coefficients, beta 1, beta 2, bn, and so on. These was intercept, like if you just look into c plus mx, y equal to c plus mx. So this c refers to beta 0, and we can have m, loss of m, and so on. So and x can be featured. So yeah, here instead of mx we have lots of them, beta 1x, 1i, and so on, right? We can have them. So yeah, this is how it works. So there are some if I just remove that linear model assumption, there are some assumptions we do have in linear models. These are the things like the model values the outcome variable for each increment of the predictor lie along a straight line. There is a linear relationship between predictors and target. So yeah, that's the predictor and target. There is a target is basically y, x is our predictor, and so on. So these are some sort of assumptions we do have. Normally distributed errors, so the errors are distributed normally, something like this. If we have errors, this is like this, or so on. You will see no perfect multi-collinearity. So there should not be there should be basically no perfect linear relationship between two or more of the predictors. So these are the assumptions we do have in general. We do look into that, and when the assumptions are met, like obviously these are assumptions we want to have. When these are met, this is the outcome we do have, like the model is a good fit for the data, and so on. This is how we get the result. When they are not met, like if we cannot meet these scenarios, we need to actually get these scenarios correct. So some issues should be, we can have outliers, we'll have lack of homoscedasticity, and the variables are too skewed and so on. What can we do? We can have like mathematical transformation, we can have discretization, we can remove or censor outliers. Okay, so as mentioned in the assumptions, you can see, as mentioned, the normality can be assessed with histograms or by q to q plots. So you can see this might be our errors. So this is 0, right? We're saying the majority of the value, like the error should have a normality distribution. That means we can have maximum in the we have learned them or working with the machine learning model. So our goal is to have least errors, right? Obviously I have talked about this, how to reduce the error and so on, cost function and so on, a lot of things. So if the error is or the cost function is very less or 0, near to 0, and most majority of the cases it happens, that means that is our goal. So you can see for error 0 with the or within 1 to -1, we have the majority. Here the graph looks like that, but for more the error 3 -3, it is not that much. So for that, you can see for these when these things happen, you might have this kind of graph, or you can say for this kind of linear regression model, this might be our error graph. Okay, now we can have a normal distribution, and again there is another concept, which is this one, homoscedasticity. So here you can see this the error term, that is the noise in the relationship between the independence variables x and the dependent variable y. It's the same across all the independent variables. The term the error term is the same across all the independent variables. So here this in this scenario you can call that. To identify this one, we need to plot the residuals versus each of the independent variables. So independent variables are x because depending on them we have y, right? So the error term is the same across all the independent variables. So you can see these are independent variables and these are residuals. So to know that, we can just have them as mentioned, plot residuals versus each of the independent variables. We just plot them, we can actually find this scenario. Okay, so here again, in general, when we're doing the machine learning or linear regression as a whole, our goal is basically to get something like this, like a line which covers most of the points we have. But sometimes it can happen that we have huge number of points and the line cannot cover them. We can have these scenarios as well. Obviously these are the scenarios we don't prefer. Basically this kind of things happen when we have a non-linear relationship between these two labels, population and price. Okay, here we do have, like for medicine and price, you can some sort of linear relationship, because you know like from the graph, obviously there's something we need to learn from, like what they're meaning. You can understand that we had some sort of values, like for x and y we have plotted these dots, then we got a connection, we created this line. Now if someone says, hey, for particular value of x can we get a y, and there's a very high chance that it will be able to detect. But for this you can see there are lots of points, right? And you can see the datas are almost here in these lines and so on, and it covered the line. So it almost looks like okay, there are more points than the line. Obviously much more values we do have some sort of a linear relationship from the graph we can look like. Okay, for some particular points very near here, it can give very good actually result. But points which are here or here and so on, this model is not good. But here you can see this is is totally like this, and the line is totally here. Maybe if the line was here or so, we could have said like, hey, it's some sort of relationship we do have, but the line is totally in different kind of stuff here. So you can say there is no linear relationship here. Linear is basically something like we can have x and y, and if we have something like that, it's a linear. You can say just one line and y equal to mx plus c. So this is the equation for that. Okay, again in linear relationship, the residual plots, if we just look into that, we have seen that earlier, and this is a residual plot, and expected simulated data, so it would look like this, something symmetric, and somewhat for this one it would not look like this. For data which we have here, you can see it's like distributed normally, like okay, but here it's not. It's like most of the data, as you can see most of the data here are distributed in the middle, right? Lots of data, so the graph is majority is in the middle, but most of them are in here in the left side. So you can see the graph is basically here, so most values are in the actually left portion, so it can be called right skewed because the tail is in the right basically. Okay, so yeah, there are a lot of things we can learn from the distribution and so on. Okay. Okay, there is the final one, which is multi collinearity. So this is basically the connection between two things. Like for example, you will see this kind of things later on. So for two different kind of labels, like for this and this is the connection. So the connection or the linearity or dependency, multi-collinearity occurs when the independent variables are correlated, somehow related with each other. Okay, so this is when this multi-collinearity happens. So yeah, linear models or something like that, we have seen that. Feature magnitude matters. So the feature magnitude, so we have these are our features, x1, x2, xn, x3 and so on. So the magnitude of the feature, like maybe for x1 we have 100, for x2 we have 2, for xn we have 1000 and more, 10,000. So the magnitude or the more value we have, or the value basically, it doesn't matter, it does impact the result. So yeah, the regression coefficient is directly influenced by the scale of the variable. These are our coefficients, beta 1, beta 2, beta 3, beta 3 and so on. Variables with bigger magnitude or value range dominate over the ones with smaller one. So yeah, which has bigger, which is like xn or x1, it dominates x2. So yeah, there are a lot of things and gradient descent converges faster when weights are on similar scale. So if the range is almost near, or like it was 2, it might be maybe 10, it can be maybe 5 or something, so it's very near, so gradient descent converges faster. So there are a lot of things. So gradient descent, we have learned that, so to reduce the cost function if it's very near, so it's very easy to actually get the less cost function or minimize the cost function. It's very fast, it will take time. This time feature scaling helps increase the time to find support vector for SVM. Scaling helps decrease the time. So we can use feature scaling to decrease the time to find the support SVM. So we have learned about SVM, and Euclidean distances are sensitive to feature magnitude. So this is one of the concepts you have learned about Euclidean distances as well. Okay, algorithm sensitive to magnitude. So there are various kind of ML algorithms who are very much sensitive to the magnitudes. So those are linear and logistic regression, Euclidean network, support vector machine, which is SVM, KNN, K-means, linear discriminant analysis, PCA, and machine learning models which are not sensitive to feature magnitude are these. Okay, so yeah, now this is a basically a table where there are various models, the assumptions as mentioned. It does have the advantages, it does have disadvantages, feature scaling it requires or not, missing data, how it handles missing data, what about outliers, suitable for which kind of scenarios, learning, supervised or unsupervised machine learning is divided into supervised and unsupervised, and example uses or scenarios where they are real life examples. So there are lots of models. You can see there are lots of models. We'll learn about them, like and when they are used. So if you just want to learn about that, you can just pause this one, and let me just give it one. You just pause this one and zoom in a bit, and you can learn about these. And I've also shared them in the Discord channel as well. So yeah, you can take this screenshot as well. So these are the scenarios, so we'll learn about them gradually. So yeah, thank you so much for watching this video, and I hope to see you in the next video.